Okay, so let's continue solving Preboard 2 for a quiz number 1, fluid mechanics. So we were able to solve last video the problems 1 to 4. So let's continue here in problems 5 to 6. So there's an open tank, 10 meters long. It is supported on a car moving on level track and uniformly accelerated from rest to 30 kilometers per hour. And the tank was filled with water to within 15 centimeter of its top when it was accelerated. So how does it look like? How does the tank look like? So let's draw the tank. So let's just say this is our tank. Okay, so maybe like that, and it's open, and it's supported on a car, or maybe at the back. So let's just put here some form of vehicle. Let's say it's a truck right there. So this vehicle here accelerated from rest to 30 kilometers per hour. So we have here motion here is 30 kilometers per hour. Okay, and it says here the tank was filled with water to within 15 centimeter of its top. So here is our 15 centimeter. So this is 15 centimeters here. Oh, this is 0.15 meter. And then when okay, so what's the condition here at number 5? Find the shortest time in which the acceleration may be accomplished without spilling liquid over the edge of the tank. So this vehicle here will accelerate without spilling the liquid inside or the water inside the tank. So what will happen here for without spillage? So let's put here symmetrical line. So here is the symmetrical line, and the water will tend to go here at the edge of the tank and goes like that. There. So that becomes the new elevation of the water. So this becomes 0.15 meter. Same is true with here. What is the rise of water here becomes the fall at this side, okay, at the front. Okay, so that becomes the new this becomes the new height of the water. Okay, and let's name this as y. So the rise and fall of the water becomes the y, and let's name this as x. From the formula, we have here tangent theta is equal to the acceleration over the acceleration of gravity equals the rise of the liquid over the horizontal distance from its point of symmetry. Okay, for the acceleration, it's not given. Acceleration here, and then acceleration of gravity, the rise of the fluid is 0.15, and the distance. This is 5 meters because the length of the truck, the tank here is 10 meters. So that's why we have x here equal to 5 meters. Okay. Therefore, acceleration here is equal to 0.29 meter per second squared. So find the shortest time, it says there. We can use that in the formula for acceleration. So acceleration times time is equal to final velocity minus the initial velocity. So where do we get the initial velocity? The initial velocity is that since the vehicle started from rest, therefore initial velocity is 0. And for the final velocity, we will use here the 30 kilometers per hour given in the problem. So we have here 30 kilometers per hour multiplied with 1,000 meter in every 1 kilometer, and that is 1 hour is equivalent to 3,600 seconds. That is second. So we have now final velocity equals 8.33 meter per second. So we have here the acceleration as 0.29 times t, the time, equals final velocity 8.33 minus initial velocity 0. Therefore, time is equal to 28.72 seconds. So from the choices, we have here the closest from the choices is letter C, 28.74 seconds. Next, number 6. The height of the water is 1 meter when the tank is at rest. Determine the total acting force on the bottom of the tank when the tank was accelerated if it has a width of 2 meters. So, calculate the total force acting on the bottom of the tank. So, let's see that. Let's redraw the tank again. Or let's draw the tank again. So, we have here tank. Then, since it's open, let's remove this portion. Then, we have the it's probably let's draw the symmetry line, and then it's probably the same situation as mentioned above. So there's no spilling liquid here. So this is our water. Meters, and then we have the width here as 2 meters. Okay, so this is the initial, remember the initial level here. We have the rise here as 0.15, and the problem mentions that the height of the water is 1 meter when the tank is at rest. Therefore, you can say that this portion here is 1 meter. So if this is 1 meter, if this is 0.15 here, so what is the height here? So that is 1 minus 0.15, that is 0.85 meter. Okay? So we need to find the, says here, determine the total force acting on the bottom of the tank. So we need to find the F vertical. So force is FV, and that is gamma volume, right? So we need to find what is the volume of the water here. Okay? So gamma volume since since there is no spilling liquid, so if there is no spilling liquid here, so you can see here that it's trapezoidal. So meaning we have here 9.81, and for the volume we have the area of the trapezoid. We have 1/2. The base here, base 1 is 1.15 plus 0.85 the base, and the width is the here it's 10 meters the width, and then we have here 2 meters, and that is equal to 1.15 plus 0.85 times 10, so 196.2 kilonewton. Now also, if you see that there is no spilling liquid involved, you can just simply FB at rest. There's no spilling liquid, right? So you have here the FB, the gamma volume here, as 9.81 times the 1 meter. Okay, 1 meter times 10 times 2. Let's see, 9.81 times this one here. So it is also 196.2 kilonewton. So from our choices, the answer here is letter C. Okay, so that's for number 5 and 6. Let's go to problem 7 to 8. An open vertical cylindrical vessel is 2 meters in diameter and 4 meters high, 4 meters high, and it is filled with water to the top. If rotated on its own axis in order to discharge the quantity of water to uncover a circular area on the bottom of the vessel 1 meter in diameter. Determine the angular rotation in RPM and how much volume of water is left in the tank after rotation or the spillage. So how does it look like? We have a cylindrical vessel, open, so it's open because we're talking about spillage, therefore we can say that the vessel is open. Okay, so we have here the cylindrical vessel. So this is the symmetry, because it says there the rotation is on its own axis, therefore means here is the rotation. And it is filled with water to the top, so it's filled with water to the top, and then it becomes, or it starts to rotate. So upon rotation, of course, there will be spillage of water. So when rotating this, the water will always be at the edge of the container, and the tendency here, okay, it will form a parabola, and okay, it will form a parabola here because of its angular rotation. and there will be a 1 meter diameter open portion here. So there's an open portion, and that is 1 meter. So here is the open portion, okay, and that is 1 meter. So the diameter of this vessel is 2 meters. Let's just put here 2 meters. And the height of this cylinder is 4 meters. And let's get also the height of the small parabola here, formed at the bottom of the cylinder. Let's name that as H. So 4 meters, and this is H. Okay, so this is the remaining water. Here, this is the remaining water. How do we get the rotation? Determine the angular rotation in RPM. The formula for the height of the parabola here. So for the height of the parabola, we have so let's name this as Y. Okay. So Y is equal to the omega squared, or the angular, it's the angular rotation, then the radius squared all over twice of gravitational acceleration. So how do we get the value of Y? For the value of Y, we need the value of H, because Y is equal to 4 plus H. So how do we get that? We can do the duration proportion for parabola. The duration of proportion for the parabola is height over the radius. So let's consider the bigger parabola. The bigger parabola has the height of 4 plus H divided by the radius of the bigger parabola as 1 meters. 1 meter, and we will square that. Equals the height of the smaller parabola over the radius of the smaller parabola, and that is 0.5 squared. So H now is equal to 1.33 meter. Therefore, from the formula, we now have here Y is equal to 4 plus 1.33. Therefore, Y is equal to 5.33. Now, from this formula here, we now have the value for Y. 5.33 equals the angular rotation squared, the radius of the big parabola, all over the twice of gravity. So angular rotation, so what's the angular rotation now? That is 10.226 rad per second. So we need to convert that first. So if it's still in rad per second, we have to multiply it with 30 over pi. That is equal to 97.65 RPM. Take note, RPM is greater than the rad per second. So if you're dealing with conversion, if you're looking here at rad per second, you know that the value in RPM is greater than the value in rad per second unit. Therefore, you need to multiply 30 over pi. Now, if you are converting from RPM to rad per second, you just need to multiply it with pi over 30 to make it smaller so that the value is smaller. The numerical part here is smaller than the numerical part, the numerical for RPM. Okay. So from the choices, we now have here 97.69 as the nearest from the answer, from our solution. Next, number 8. How much volume of water is left? So, how much volume of water is left in the tank after rotation or spillage? So, how do we solve this? So, for volume left, so that is for number 5. For number 6, for volume left, if you analyze it, it is equal to what? The volume of the cylinder minus the volume spilled. Okay, so how do we determine the volume spilled? For the volume spilled, we have the bigger parabola. So the volume spilled here is this portion. So look at this. So this is the volume spilled. Volume spills. How do you compute that part there? That will be equal to the volume of parabola that is bigger minus volume of parabola that is smaller. Or let's say volume of parabola big and volume of parabola is small. Now, what is the volume for parabola? Volume for parabola is 1/2 pi radius squared and the height, the y. Okay, so that's the volume for parabola. Let's do that here. Volume spilled is equal to volume of the bigger parabola. So for the bigger parabola, that is 1/2 pi. The radius of the bigger parabola is 1 squared, and its height is 4 plus 1.33, it is 5.33. Okay. Minus the smaller parabola, 1/2 pi. The radius here is 0.5 squared, and the height of the smaller parabola is h, and that is 1.33. So volume spilled now is equal to 7.85 cubic meter. Therefore, volume left is equal to, the volume of the cylinder is pi r squared times the height minus 7.85, that is equal to 4.72 cubic meter per cubic meter. So that is 4.72 cubic meter. So from the choices, the nearest here is letter C. How much volume of water is left in the tank after rotation or spillage? So that's for number 7 and 8. Now for the last problem, for the quiz number 1 under the topic fluid mechanics. So there's a concrete dam retaining water shown. If the specific weight of concrete is 23.5 kilonewton per cubic meter, so find the factor of safety against sliding and find the factor of safety against overturning if the coefficient of friction is 0.48. So given the gamma of concrete as 23.5 kilonewton per cubic meter. So for the so remember that for the factor of safety against sliding, the formula there is mu RB over RH, right? And for factor of safety against overturning, we have righting moment over the overturning moment. That's why if your factor of safety is below 1, that means OM, or that means OM is bigger than RM. So the safe here is it should be RM should be greater than OM for safer structure. And that for factor of safety against sliding, mu RB should be greater than the R horizontal. Okay, for this figure, we will need to find the weight 1. Okay, so this is weight 1 for this rectangular portion, and then this is weight number 2 for the triangular portion. Then we have here F as the horizontal force of water. Okay, so there's no mention of uplift force. Okay. So what's the value for weight 1? Weight, or W, is equal to gamma volume, right? So weight 1 is equal to gamma of the concrete 23.5 gamma volume. So volume here is 2 times 7 times 1. So we're dealing with per meter width. And that is equal to 329 kilonewton. For weight number 2, that is 23.5 gamma of concrete. Then we have the volume of the concrete here is 1/2. This is the base here is 2, the height is 7, and then per meter width. And the answer here is 164.5 kilonewton. Now for the force F, there, the force F, the formula there is gamma HE. That is 9.81 times the gamma of the liquid, the gamma of the water times the bar H. So where is this bar H here? So if you have your eyesight here on side view, you're looking at a figure like this. So the width, it says there the width is there, per meter width. Okay, so this is 1 meter. How do you get the center of gravity of this one? So it says there gamma H. So the center of gravity here is 3. Meters. So 9.81 times the bar h, which is 3 meters. And then we have the area. So what is the area? That is 6 times 1. So 6 times 1. So the answer here is 176.8 kilonewton. Okay, so for factor of safety against sliding, mu RV RH. So that is, what's the mu? What's the value for mu? Coefficient of friction. That's the mu here. Coefficient of friction here. So we have here 0.48 times the RV. So R vertical. R vertical is 329 plus 164.5. So these are the vertical forces. So we have to divide it with the RH. The RH here is 176.8. 0.48, 329, 1645, 176.8. So we have so it's 58, 329. So 1.34. So factor of safety against sliding is 1.34. Next factor of safety against overturning, that is righting moment over overturning moment. So from the figure, the righting moment, or the forces, you are to consider the forces that will make your structure stable. So what force will cause the structure to be stabilized? That is the weight of the structure. Now, how about the overturning moment? So it involves forces that tends to overturn the structure. So here in the figure, we have that as the force F of the water. So the water here tends to overturn the concrete dam if it becomes too strong for it. So here, for our factor of safety, our righting moment. So since we're dealing with moments, so we need to have the distance of these forces from the toe. So the question, where is the toe? The toe is here. So can you see this portion? That is the toe. Wherein, if the force of water begins to push this structure, so where does it tend to rotate? So it tends to rotate here. So it has a tendency to rotate in this portion. Okay. So that's the kind of failure that we're trying to avoid. So the distance from this W1, weight 1 of the rectangular portion, so that is 3 meters. this is 3 plus 1. So 3 plus 1 equals 3 meters. How about weight number 2? For weight number 2, that is 1/3 of 2. So what is 1/3 of 2? 0.667. No, it's not 1/3. It should be 2/3. So 2/3 of 2. So 2 times 2 divided by 4. So it's 1.333. So here we have 1.33. How about force here? The force here is 1/3 of the total height. So 1/3 of the total height, that is 6 divided by 3. So this y here so y here is 6 times 2/3. It should be 1/3. Sorry. It should be 1/3. That is 2 meters. Okay. So times 1/3. Therefore, our writing moment now, since we have now the distance, so writing moment that would be, the weight one is 3.29 times 3. Plus, the writing moment for weight number 2 is 1.33. So weight number 2 is 164.5 times, what's that? Yeah, 1.33. Divided by the overturning moment, which is the force 176.8 meter. Ah, 176 times 2. Okay, the distance. Okay, so the answer here is 3.41 and it's unitless. And the answer here that is nearest is letter B, 3.42. Okay, so that's for number 9 and 10. Okay, so that's all for the video for the solution for Preboard 2 4A quiz number 1, fluids or fluid mechanics.